Yeah, I'm going to talk about an algorithm that we developed in Munich regarding the computation of line bundle cohomology, so sheaf cohomology, over Toric varieties, and well, some applications which have been developed subsequently. So it's basically the algorithm was conjectured originally in March last year. A couple of months later, it was proven, once in our group and once from completely independent source, apparently here from the UPenn, which we never met actually. And well, a couple of months later, actual further applications were considered. First, as a motivation, why do we even care about line bundles and line bundle cohomology? Well, line bundles, or in general cohomology, are rather abundant in string phenomenology. For example, pure line bundles frequently appear in type 2b orientifolds, where you deal with abelian fluxes or have to compute a chiral spectrum in that context. Then in type 2b or F theory constructions, for example, the consideration of instanton zero modes frequently involves line bundle cohomology groups and fluxes as well. Another important point is that vector bundles can rather easily be constructed from line bundles, in particular holomorphic vector bundles. For example, there is the famous monad construction, where you take direct sums of line bundles, two direct sets of sums of line bundles, and then indirectly construct a monad, which can also appear here if you dualize the entire sequence. And for example, the tangent bundle of a toric variety can easily be described as a monad, and as can be derived from that point, you can compute vector bundle moduli, which are countered by the endomorphism bundle, and you can dissect this also into a couple of short exact sequences. So one important point is that you actually can dissect whatever you want to compute into short exact sequences. And this is basically the reason for that. Once you have a short exact sequence of line bundles, as has been drawn here, as has been written here and colored appropriately, you simply consider the induced long exact cohomology sequence, where of course then the line bundles appear as the actual value groups with the appropriate decomposition into the direct sums. So the idea is here, let's assume I want to compute the sheaf cohomology with values in the tangent bundle, and I have the monad construction of the tangent bundle. Well, then I can, in principle, using the exactness which I have in this case, compute those two cohomologies here, and ideally, if there are enough zeros appearing in those constructions, or if I do the laborious way and actually compute all the mappings in between, can derive well, the cohomology with values in the tangent bundle from that. So in the luckiest case, everything boils down to computation of line bundle cohomology, and this computation can sometimes be quite laborious, and this was one of the main motivations why we devised a new algorithm for that. Now, I'm going to very briefly describe this algorithm construction. So the ultimate goal is to find a very easy way to compute the dimension of sheaf cohomology groups as written here. The input data is a plain good old toric variety, so we have a bunch of homogeneous coordinates, the associated GLSM charges, and the Stanley-Reisner ideal, which plays a really central role in our algorithm. So those calligraphic S's here are actually the generators of this Stanley-Reisner ideal. Now take a square-free monomial Q in those homogeneous coordinates. Then one of the main objects in our algorithm are monomials of this particular form. So you take the square-free monomial, and the coordinates appearing in it, or rather as a product in it, appear in the denominator of those monomials. Then we consider monomials in those coordinates also in the denominator. So basically, the coordinates which you have in your square-free monomial have at least the degree -1, and the complement of those have all positive degree. This is the basic structure of those monomials, thus the coloring. Now, those monomials, of course, well, as a monomial, each coordinate has a GLSM charge, so you can compute the GLSM charge of the entire monomial in this form. What we are taking, as we want to compute the cohomology of the line bundle associated to this divisor. This divisor has a GLSM charge. What we are counting are the number of monomials of this particular form which have the same GLSM degree as the divisor of the line bundle we want to compute a cohomology from. So we count the number of those monomials, but now we have the problem. Once we have this number, yeah, well, it's nice and fine, but to which actual group does, or which group dimension does this actually contribute? In order to determine where this number contributes in the counting of dimensions, we need to trace back how often or in which ways the same square-free monomial Q can actually be constructed from a Stanley-Reisner ideal. And in the original conjecture, this was all a bit, well, obfuscated due to our actual lack of a precise formulation, but it turns out this is a rather simple structure. From the Stanley-Reisner ideal, you can simply consider subsets of the generators, and, well, you consider basically, for each square-free monomial, you build up an abstract simplex of all the subsets of Stanley-Reisner ideal generators, where the union of their coordinates, well, we've built the square-free monomial of which you form this abstract sequence. And then you can simply split it up into k phases by simply dissecting it to the number of Stanley-Reisner ideal generators which you unified. So this is just subsets of Stanley-Reisner ideal generators which give you the monomial in question, and then you decompose it into, well, how many Stanley-Reisner ideal generators did I unify? And once you have built up those k phases down here, what you do is consider a boundary mapping. Well, for a complex, of course, you need mappings, and those are actually pretty simple boundary mappings. This is nothing else than taking an ordinary simplex boundary. So what you have is the sum. So if this is a basis vector representing a certain subset of Stanley-Reisner ideal generators, what you do in the boundary mapping is consider the sum of all possible, well, let's call them subsets, where you remove subsequently one of the generators. And the sign, of course, basically takes care of orientation, does the drawing to somehow give you a nice image of what is actually happening. Now, this defines the boundary mapping of the complex, and the multiplicity factors, as we called them in the original paper, and still call them, are now then simply the cohomology of this complex, and they determine to which group the monomials which we counted, the monomials of this form which we counted here, to which cohomology group they actually contribute. So what you do is, from the complex, you consider the reduced homology, which means that for point-like sets, you simply set the homology group 0. You compute the dimension of this cohomology group, and as you know, which was more or less the reason for the obfuscation of our original papers, we have here a homology structure which goes down in the degrees, whereas in this counting here, where the E increases due to the minus sign, this one goes down. So the important point is basically that those factors here tell you, well, the numbers which I counted here contribute to the cohomology group of, well, if I want to compute HI, I consider this number here, and if it is 1, or basically un-0, to this group it contributes. In fact, in most cases, this number is either 0 or 1, but not in all cases. And in fact, as a very dirty speed-up trick, which we are using quite frequently, it suffices to simply compute the dimension of those phases which are introduced here, and not to consider all those mappings. In fact, we don't do that. And this gives you a huge speed-up. With a couple of dirty tricks, you can really speed up the computation and get exactly the same result. So the algorithm is basically nothing else than a sum over square-free monomials, which you get from considering unions of Stanley-Reisner ideal generators, and then sum it up as the multiplicity factor and the counting of the monomials in the forms I showed you earlier a couple of times. And yeah, well, this is basically our time. Determine all monomials Q, which you can get from unions of Stanley-Reisner ideal generators. For each such square-free monomial, you compute the phases of the associated simplex. Then from that, mostly using this dirty trick I just mentioned, you compute the multiplicity factors. And then, of course, once you know, okay, the multiplicity factor is 0, so whatever those monomials don't contribute at all, for only those which are non-zero, you actually do the counting of the monomials, of the rational functions, and then you sum it all together. And The very important point about this entire procedure is that it is completely algorithmic. Usually a lot of cohomology computations you do are extremely dependent on your actual geometry or your actual configuration. You try to relate stuff to known results, well, which might work or it might horribly fail. This procedure is entirely algorithmic, so it can be really applied to all toric varieties. Of course, if stuff gets a bit more complex, you really have to work out the actual mappings, but this is more or less a problem of how many labor you want to put into it. It's not a principal problem. Up to this point, it's completely well defined and completely algorithmic. So now what to do? Of course, toric varieties are interesting, but at least from the point of physicists, string theorists, they are only small fractions of the material which actually interests you. For example, a very important class are hypersurfaces. For example, the quintic, which was one of the most important Calabi-Yau threefolds ever devised or ever found. Well, it's a hypersurface, it's not a toric variety. So the next question would be, okay, now we have a nice and fancy way to compute the line bundle cohomology for an ambient, toric ambient space, but how do we get to hypersurfaces? And for a long time, there has been the so-called Koszul sequence, which basically relates the ambient space cohomology to the cohomology on your hypersurface. What you basically do is, well, you select a divisor in your toric variety, which is S in this case. Note that it appears here, everything which is red has the S in it, of the toric variety X, and let T be an arbitrary second divisor, and then you see the T appears everywhere. So you can basically compute every divisor T of your hypersurface by relating it via the Koszul sequence to the ambient space. So, and since we easily can compute this part now, naturally we can compute this one. Also, just by doing exactness considerations of those long snake lemma I showed you earlier. So this is one very helpful, but of course a bit laborious step. And in fact, by iterating this procedure, by going first to a hypersurface, then a hypersurface of the hypersurface, and so on, you can also compute, for example, line bundle cohomologies on complete intersections. This is basically just iteration and bookkeeping, but we come to that later. Well, not that much later. Another important point, which has been considered in the application paper is, well, since we have very explicit monomials which we are counting in this ND contribution here, we have a kind of representatives for our cohomology group, not precise representatives, remember, because those multiplicity factors, they are often 1 or 0, so basically they are just 1 if they contribute, but they can be 2, 3, or any other natural number in principle. So those are not precise representations, but can be thought of that for the most part. So considering that we're counting rather explicit monomials, one can consider, well, what about if we have involutions on our toric variety, some kind of symmetry? We can very simply apply this symmetry mapping, which is defined on the base space of our toric variety, directly on the monomials which we're counting in the computation of the line bundle cohomology, right? Well, first we have to actually uplift the symmetry defined on the toric variety to the bundle. This is called a so-called equivariant structure. This basically just tells you when you have a base involution, G here, it has to be lifted to an actual bundle mapping, so a mapping of the line bundle. And of course, it has to be a group homomorphism, so the group structure has to be preserved. Then it's called an equivariant structure. Absolutely simple consideration. It's just the sensible uplifting of your base involution to the bundle. And however, an important point is at this stage that projectively equivalent involutions on your toric space give rise in general to different equivariant structures on the bundle. So if you simply take the mapping you have defined on your toric variety and apply it to the monomials counted for the line bundle cohomology, this in general will give you different results. And this is important to keep in mind, because the formalism, when you do the explicit computations, easily gets you mixed up in that aspect. I should probably mention that this generalization was actually considered earlier in a paper by Cvičić, Garcia, Etxebarria, and Halverson. Well, they came first, at least for
structures. You said that for the same atom on the base, you have different uplifts to the bundle.
Yeah.
But those equivariant structures on one bundle should be unique uplift character. So I'm just wondering what is the difference that you see?
We had a lot of trouble when we were first considering those, because we completely ignored that there are different equivariant structure. So we did the plain computation and noted that there were a lot of switching between the monomials. What actually changes is not the end result which you compute here, but which monomials contribute here. So if you choose different equivariant structures, suddenly monomials become invariant which haven't been before and vice versa. And this is basically what changes. You might say the equivariant structures are not that important in this actual computation here, but in the intermediate steps it becomes important. So this was more or less take care if you do this by hand.
Okay, my question, I don't know, maybe it's one of your collaborators or yourself. How are you planning? I think you have done some conversion of all of this data into particle spectrum, into cohomology, and potential and so on. Are you working towards that? Is that also implemented as a program?
So you mean to ease up the computations which are most relevant to physicists?
Right.
Actually, that's not yet on the agenda, but there are actual physical applications which are done right now using this package in its original form. But that might be something one could consider. So.
Well, I think Ralph Blumenthal in the previous versions they have done some of that. It would be nice.
Yeah.